In this lecture video, we're going to discuss capacitors in AC circuits. Now, when we talked about inductors, we started from the EMF side. When we talk about capacitors, we're going to start from the current side. So we know that current is equal to dq dt. And we know from the beginning of this chapter that we're going to say that the max current times the cosine of the angular frequency times time is going to equal the current at one particular moment. Alright, so we're going to rearrange this so that we can integrate. So I'm going to integrate from 0 to q on this side and 0 to t on this side, so we get that q is equal to 1 over the angular frequency times the max current times the sine of the angular frequency times time. We know from chapter 24 that charge is related to capacitance times voltage using this relationship. We learned it as capacitance equals the ratio of Q to V. I've just rearranged it algebraically. So I can make a substitution for Q. So we're going to say our voltage is equal to 1 over our frequency times the capacitance, and then we're going to have our max current times the sine of angular frequency times time. So very similar to what we did before. Remember, we have V equals IR. So we're going to take what is up front here and put it in that same form. So we're going to have max voltage across the capacitor this time is equal to the current times 1 over the angular frequency times the capacitance. So we're going to say that the max voltage is equal to current times our capacitive reactance this time. So we can see here that the capacitive reactance is equal to 1 over your angular frequency times the capacitance. So that means we can rewrite this now as the max voltage across the capacitor times the sine of our angular frequency times time. However, we want to believe everything in terms of cosine, so that's the same thing as the cosine of our angular frequency times time minus pi over 2. Alright, so we saw when we were talking about inductors that with an inductor, the max voltage across the inductor leads the current. Here we're going to see that the max voltage across the capacitor is always going to lag the voltage. So you have omega t, so how far t has progressed, and thus how far your angle has gone up. So your current is rotated here. And so you're going to see there's this 90-degree angle, and they're going to stay in phase with each other. So this is a phasor diagram again, where as this rotates around and as time progresses and this angle gets bigger, this distance between our angle and between the current and the voltage is going to be 90 degrees. So we say that the voltage across the capacitor lags the current. And you can see that here in this diagram here, where you're sloping downward with the current, while the voltage across the conductor is peaking. Alright, so we're going to find that capacitors are, in an AC circuit, act like a high-pass filter. So your capacitive reactance is proportional to the inverse of the angular frequency or inverse of the frequency. So this means as the capacitive reactance goes up, frequency goes down. Or as this goes down, it's because this has gone up. And we know that current through this form of Ohm's law that we're using is inversely proportional to the inductive capacitance. So as this goes up, this goes down, current goes down. As our inductive capacitance goes down, angular frequency has gone up. So that means our current has gone up. So this means that you get a low signal, so low current, when the frequency is low, and you get a high signal when the frequency is high. So that's why we call it a high-pass filter, because it gives you a signal when the frequency is high, and it doesn't give you much of a signal when the frequency is low.